Tom. Hello. Hello, can you hear me?
Yes.
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 All right, very good. How are you all doing?
I'm good.
Drained.
I know you're excited. It's almost done with the lecture.
It kept kicking me out. That's why.
That's we're about to begin. I will share my screen with you now. Oh, you just give me 1 minute. What's 1 minute? 1 minute. I gotta take care of this. Remove this. Okay. I hope you can see the screen now, right? Hello, you can see the screen?
Yes.
So today we continue with our z-test for the mean. Yesterday I introduced an example with Miss Fogg, can you mute yourself, please? Okay, good. We did an example for the traditional method, and today we will continue with this same test statistics, and we'll be using the p-value method. P-value simply means the probability value. So the p-value is just p-value is a way of saying the probability value. Probability value method. Yeah. Now, for the p-value, we use the same test statistics. I said at this time we'll be using p-value instead of critical value. So the process is still the same. The only difference that here we're using the p-value instead of the critical value. So the same process which involves stating the hypothesis and identifying your claim, computing the test value using this test statistic, then find the p-value, make a decision, and summarize. Now, how do we summarize, make a decision here? The criteria for rejecting or not rejecting is if the p-value is less than or equal to alpha, then you reject. So it's the opposite of the other one. The other one say if the calculated value is greater than the critical value, you reject no hypothesis. But here, if the p-value is equal to or less than alpha, reject no hypothesis. But if the p-value is greater than or equal to, sorry, is greater than alpha, do not reject. So unlike the traditional method, whereby if the calculated value is bigger than the critical value, you reject. Here, if the p-value is greater than the alpha, you reject. So we do not reject no hypothesis. But if the p-value is less than or equal to the alpha, you reject no hypothesis. Let's see how this works. We're going to use an example. Let's use this example here. It says, a researcher wishes to test the claim that the average age of lifeguards in Ocean City is greater than 24 years. You can see the keyword is greater than 24 years. See the keyword right there. So she selects a sample of 36 lifeguards and find that the mean of the sample to be, excuse me, my paper notebook. The mean of the sample is to be 24.7 years with a standard deviation of 2 years. Is there evidence to support this claim that alpha 0.05 is a use the p-value method? Our solution, first of all, we state on our hypothesis and then identify our claim. Say, he want to tell the claim that the average age of lifeguard in Ocean City is greater than 24 years. So let's say have HO and H1. Now, greater than symbol can only be used in the alternative. So we have it this way, that the mean, okay, mean is, I say greater than, so you're gonna use greater than, okay, 24 years, which is the claim. Okay, now the opposite of the claim is that the mean is less than 24 years. However, we cannot use the less than symbol here. So we use the closest symbol to less than. That case, we're using less than or equal to. Excuse me, it's gonna be the mean less than or equal to 24 years. 4 years. Okay. So we have stated the hypothesis and identified our claim. And our alpha is 0.05. Alpha is 0.05. So we're gonna put it here. From here we can get our p-value. So that p-value now becomes equals. Now, to get the p-value, remember our chart that we use for this. Let's make our chart first. Or the chart, direction of the chart will tell us where to put this. So we have it in this form. Okay. What did I lose? Okay. Okay. Now, then we add this. Okay, and then put the 0. Okay. The mean of standard, so which is the 0 mean. Okay. Now it says greater than. That means it will be on this side. This side is less. This one is greater than. So I'm gonna put it here, 24 years. So I'm gonna put the critical region right here. The area where it falls. Now we have this. Okay, this is where we have our C value. Okay, from which we get our P value, our P value. Okay. Okay, almost done with this drawing. 2 more, and we're done with it. Okay, this last one. Okay, so it's greater than that. Now, so that our Z, well, do I have to be here? So the P value, we cannot get that P value right now because we need to find our get our Z first. Z, remember the formula for Z? The formula is this. I'm gonna move this down. Z equals. Oh, excuse me. The formula is right here. I think I copied it. That's right here. Z equals X bar, which is sample mean minus population mean divided by standard deviation over N. Now, our sample mean is, said, a researcher wishes to test the claim that the average lifeguard in Ocean City is greater than 24 years. He selected a sample of 36 lifeguards. and find the mean for the sample to be 24.7 years. So I'm gonna write this down so I can get the sample mean. Write this down. So sample mean is X bar is 24.7 years. 24.7 years. Okay. So let me go and get the character for it from the other workbook. Sample mean will be, okay, X bar equals 24.7. So I'm gonna put it right there. 24.7 years. A computer fools. Okay, it's open now. I think this should be it right here. So 24.7 years is right here for the sample mean. Okay, the population mean says mean is that the average age for the lifeguards in ocean cities, for all the oceans lifeguard in ocean city is 24 years. So that's the population. So mean is 24 years. For that one, we can get a character from here. Mean is 24 years. Okay, which is 24 years. And standard deviation are delta, which will be for the population. You say the standard deviation is 2 years. Put 2 right here. And how many of them were selected? It says he selected he selects a sample of 36 lifeguards. So N is 36. N equals 36. Now, when you plug all this into this formula, you're gonna get this. To make it fast, I'm gonna copy this formula, put it right here. So let me write all this down. Mean is 24 years, standard deviation is 2, and sample size is 36. So I'm copying this here. I'm going to plug these numbers in to get our Z here. Okay. Then minus, so let's plug in the numbers in, equals, put this in, which is 24.7 minus 24 divided by standard deviation of 2 over the square root of n divided by the square root of 36. 36. That would be equals, now we can plug this into our formula. Z equals X by 24.7 minus 24 divided by standard deviation of 2 over square root of 36. So once we plug this in, we'll be getting our answer for Z. So let's get it in our calculator. We have this 24.7 minus mean of 24 divided by standard deviation of 2 divided by the square root of 36. Close it. So I got 2.1, which is 2.1. So I'm going to copy this, put the answer in that workbook, and then copy it into our main workbook. 2.1, basically 2.10. So I'm going to copy it. Okay. Now right here. Okay. So copy it and put it right here. So 2.1. So we have run the test to get our Z equals 2.1. With this Z 2.1, we can now find our p-value. So I'm gonna get a p-value now. So p-value now becomes so this is a z right here, which is at the tail, 2.10 at the tail. See right here, so the tail. I think I explained it already. They call this section the tail, and this is this way, tail of the chart. So whenever it has a tail, you do 0.5 minus the answer you get from the table, provided you are using this table that we are using for this class, this one. If you're using a cumulative table, that's a different case. That means you have to learn how to use that type of table. So now, having explained that, we can now get our p-value by doing 0.5, 0.5000. Why are we doing that? Because, like I explained, when we are doing normal distribution, half of this is 0.5, half of that is 0.5. So if you're looking for only this portion, only this part of 0.5, you're gonna subtract whatever you get from the table from 0.5 minus, so let's look for 2.10 on the table of normal distribution. 2.10. Say this is 2.1 here under 0. So you have 2.10, that's right here. See, 0.4821. Write down 0.4821. So that our p-value will now becomes 0.5 minus 0.4821. And that gives us 0.5 minus that. We go to decimals and calculate and get it. 0.5, 0.5. This is blocking here. 0.5000 minus 0.4821. 0.4821. This gives us 0.01, 0.0179. 0.0179, what we write there. 0.0179. So that's our p-value right there. Now we can make our decision. So again, in summary, we have the hypothesis stated. This one is a right tail test, have our alpha. Then we draw our chart, and then we calculated our z value by plugging these numbers for the mean, sample standard deviation, sample mean and population mean. There's population standard deviation, and there's also the sample size. Then we got our p-value. Next thing is to make a decision whether to reject null hypothesis or not to reject it. So the decision is like this. Remember the decision criteria. According to the p-value method requirement, we reject if p-value is less than or equal to, equal to alpha. Reject null hypothesis. But if the p-value is greater than or than alpha, do not reject. So our p-value here is this decision here. Decision time. Okay. We have our p-value equals 0.0179. And our alpha was, what's the alpha? 5%, so 0.05. So we'll copy it on here. Alpha is 0.05. Okay. Which of these things two are, which of them is larger? You can see that which of them is larger? When you look at them, if you compare them, you see that the p-value is less than alpha. It's less than 0.05. So that means reject the null hypothesis, which is HO, because the p-value of 0.05, sorry, of 0.0179 is p-value is less than the alpha. It is less than the alpha, of 0.05. So that's how why we reject. So which means that we are rejecting a null hypothesis. If we are rejecting, that means the claim is correct. So which leads us to make a conclusion. Conclusion. There is sufficient evidence to support the claim that, what was the claim? That the average lifespan of patient city is greater than 24 years. So which means that the average average age of life guard in patient cities is greater than 24 years. Right here. So that's the average is greater than 24 years. Questions? Any question?
No.
Good. Now, I want to explain something more. If this is a two-tailed test, like if this is equals and not equal, that means we are going to multiply our p-value by 2 to get the actual p-value. But because this one is not a two-tailed test, it is a right-tailed test, we don't have to do that. So we leave this p-value as it is. So if it's a two-tailed test, we multiply the p-value.
What's the two-third test?
Remember the one you do yesterday, when you have put this side shaded and this other left side shaded, and the null hypothesis and alternate hypothesis would be like this. You have what mean equals that.
Right.
It's not equal to that. In that case, that means you're gonna share both of them. In that case, in that case, your p-value answer will multiply by 2 to get the actual p-value. Okay?
Yep.
But this one is not tailed test. That means you don't have to do that. Okay? It's a right tailed test. So you just use the p-value you get from the table where it is, without any change. Okay? Question? So there's no question. So the other one, which is this one here, you can try at home as a practice. Let's look at the other type of tests. It is called the t-test for the mean. We use the t-test for the mean when the population size is small. That means when we say that it is small, we have that the n is less than 30. And also, we do not know the value of the population standard deviation. So in that case, we're going to use the t-test. The formula is still for the test statistics is similar, except that we'll be using the sample standard deviation. And this side will be replaced by t. And also, we will not be using the z table. We'll be using the t table, student t distribution table. We have met this table before when we were doing our confidence interval for the mean for small sample. In that case, we use the degree of freedom, and also the different values for alpha level. For example, for 2 tails, we use this one. But for 1 tail, we use the A and 1 prime. But for 2 tails, we use A plus 2 primes. That's the alpha level. Here, these are alpha levels. Here is where you are. Is it 125? That means you are how many percent confident? Probably 125 and 100 minus but in fact, about I'll say some 75% confident, probably. This one is 100. We are 90% confidence. This is for one tail. For this one, you are 0.075. That means about let me see. Let me check it. 1 minus 0.075. 1 minus 0.075 will give us the let me see the how confident you are. 1 minus 0.075. So you're 92.5% confident, you know, for that. Now, the same thing for even it is two tails. You know, using all these numbers here. This is for 80%, this is for 90%, 95%, 98%, and so on and so forth. So this is, let's do an example of that, where we don't know the sample size, and we don't know the value of the population standard deviation. We'll try the example for that. So look at the first example. It says a job placement agency. A job placement director claimed that the average starting salary for nurses in year 2000 is $24,000. A sample of 10 nurses' salaries has a mean of $23,450 and the standard deviation of 400. Is there sufficient enough evidence to reject the director's claim at alpha 0.05? Solution. The first thing is to state the hypothesis, identify your claim. So let's start with setting the hypothesis HO, null hypothesis, and H1, which is alternative hypothesis. Now, it says a job placement director claimed that the average starting salary for nurses in 2000 is. Excuse me. Now, is means equal. So you're gonna be here, mean, because you can only use equal sign in the
Professor Oza.
Huh?
I just wanted to let you know it's thunderstorming outside, so if something's wrong with my internet or like the power goes out, then it's because of that, and I didn't leave. I just wanted to let you know.
Something is wrong with your internet?
No, I said if that happens because it's thunderstorming outside.
I was gonna say the same thing because my light's blinking now.
Right.
Okay.
Is it not thundering where you are?
Well, maybe I'm inside the house.
I am too. I can hear it.
Yeah. What part of Baltimore are you at?
Baltimore City.
Well, I think I saw on the news that they're going to be thunderstorm this evening.
Oh, okay. I mean, I just wanted to let you know, just in case, you know. So he's like, oh, she's not here. She didn't come to class.
Well, if you disappear, that means you didn't come to class. What? How about that? I'm playing with you. I understand. So the mean.
So I'm sorry, real quick. You said is means.
Yeah, because it says here, see, there's a keyword right there. Say that the mean, that the average starting salary for nurses, okay? The average, just the mean, okay? Average starting salary. Say is. These two things are the keywords. Say is means equal, okay?
Okay.
Is means equal. So it is 24,000. So, and we can only use the equal sign in the null hypothesis. 24,000. Okay. That is where the claim is. So the opposite to that becomes that the alternative, which said that the mean is not equal to. We always say the opposite. Mean is not equal to 24,000. Yeah. 24,000. And the alpha they use is 0.05. Remember, that means just you are 95% confident. So even if there's going to be type 1 error, it's just going to be only 5% chance of having that. So now, our sample mean, let's get the sample mean. It said a sample of 10 nurses. You can see that the sample size is small, 10 nurses. See, that's tell you that, see, we are using the test where the sample size is small, that is less than 30. And we don't know the, for this particular sample of 10 nurses, the sample mean becomes 23,450. So we're gonna put 23,000. So sample mean, let's get the sample mean from the other book. The sample mean, which is X bar. Oh, I should have written it down. Okay, let's see. Sample mean is X bar, okay, which is put it down somewhere. Then have it written down somewhere.
Oh, it just blanked me out. I gotta go.
Really? Like it's thundering, like thundering outside.
Oh, try and be safe there, okay?
Bad.
Okay, be safe. Hello, you can hear me, right?
We can hear you.
I think we lost Miss
I can
Rita.
hear you.
Yeah. I can
Sample
still-
mean is 23,450. Okay, 23,450. So I'm gonna copy it so we can put it right there. 23,450 for the sample mean. Okay, that is right here. All right. Now, sample standard deviation we're using is 400. So S sample standard deviation is $400. So we have our sample size, sample standard deviation, and what again for this population mean, we have it already as 24,000. So the population mean is 24,000. So I'm going to move this thing down so we have enough room to solve this. Okay, let me move it down. Have plenty of room. Okay, good. Now we can now transform this, run the test using the test statistic formula, which is this one here. So let's run it, plug all these numbers in. Let me write them, all of them down so we can plug them in. Some population mean is 24,000. And the sample standard deviation is 400, and the sample size is 10. So I'm gonna plug these numbers in, and get our results. Okay, so that we have it here. Equals have 23,450. 450 minus 24,000 for the population mean. Okay, what about standard deviation of 400 by square root of 10, and that gives us this result. And from this most, we have, let's go to calculator and get the result. We have it as, okay, sample mean of 23,450, population mean of 24,000, okay, divided by standard deviation of 400, divided by square root of 10. Okay, give us negative 4.3 say 4.3481. So just about the second decimal place,
But it's
4.35.
negative.
Yeah, it doesn't matter. Remember, this is a two-tailed test. Two-tailed test means that it can be on the left side, which is negative,
Mhm.
and the right side. See what I mean?
Yeah.
So negative 4.35, negative 4.35, right there. Negative 4.35. So I'm gonna copy this and paste it in our main workbook. I think this is a main workbook right here. So we have our test. See, so now remember, this is a two-tailed test, which means left and right. So I'm going to draw the chart here. Let me draw the chart here. Include the shapes, and that will show you the two tails, and then up, and then down. Okay. Now put on this one here. We have this, and the middle, which is the zero up here, 0 here, and then okay, this is good enough. I think this is good enough. Now, okay, got it. So let's shade it, because this is two-tailed test. That means it's going to be shared two sides. I'm going to put this side as here, and this other side, okay. Then shade both sides because it's two-tailed. Left side is negative, and right side is positive. But negative symbol is just to tell you that it is on the right side, sorry, on the left side. That's all. It doesn't mean at the end of the day, we'll be using the absolute value. The computer is a little bit slow today. I don't know why. So I'm gonna shed all this. Now on the right side,
Maybe but it's thunderstorming.
probably, and then have this, share this. So because, like I said, because it is two-tailed test, the answer can be the critical value in plus or minus. Now, okay, this is our negative 4.35 should be on this side. So I'm gonna make it negative 4.35 is right here. It can be negative 4.35, and here will be positive 4.35 because, like I said, it is two-tailed. Now, see? Now, so our critical value now become critical value. Our n is 10. So that the degree of freedom will be n minus 1, which is 10 minus 1, which is 9. So that the critical value, which is t critical, will be, I'm gonna correct t, it always does that, t critical, okay? Maybe from the table of t distribution, we can get it under 9 degrees of freedom. Remember that our alpha is 0.05, and under 9 degrees of freedom. So we can go to our table, alpha 0.05, say the df right here under 9. 0.05 is right here. You can see for two-tailed tests. See a double prime here. So for with 9 degrees of freedom, it's right here. If you go down, you will see that it's under 0.05. It's gonna be here 2.262. I see right here under 9 degrees of freedom. So 2.262.
So
two-
question, how did you figure out it's supposed to be a 0.025 and then go down at 2.262?
I forgot it is going to be 0.05
Yes, at first.
because we are told in the question that the
Mhm.
alpha is 0.05.
Okay, I got you. Thank
So
you.
you're welcome. So we have it as 2.262, 2.262. So our critical value will now become plus one because it can be left or right, as I showed you on the screen. Critical value becomes equals, I'm gonna put it right here, plus or minus 2.262. Yeah. Now we can now make our decision. So like now, if because one of them is negative and we are interested in the absolute value, so decision will be since we have the critical value, TC critical value yeah, TC equal plus or minus, we just use our answer is negative 4.35. So we'll be looking at only the side that is negative. So we have negative 2.262, which from your algebra class, the absolute value of this number is simply 2.262. And then our calculated value, the answer we'll have, which is calculated value equals negative 4.35, which the absolute value for that is simply 4.35. So since the calculated value of 4.35, sorry, 4.35, which is actually negative 4.35, which is have the absolute value of 4.35, which is what you consider. It's exceeded, is greater than the critical value of negative 2.262, but we are using the absolute value of that 2.262 because you know in algebra, even though this one is smaller, it's actually bigger than this one. So that's why we're using the absolute value. Since 4.35 is greater than 2.262, we reject the null hypothesis. See, we reject the null hypothesis. So that means we are rejecting the claim, which means that the claim is not correct. There is not sufficient evidence to support the claim. So our conclusion now becomes there is insufficient evidence to support the claim. Excuse me. The claim was that the average starting salary of nurses is 24,000. That the average starting salary, those of you who are nurses know that it's bigger than that. Information from a reliable source made me understand that nurses, people who are nurses, are very rich. Am I right or wrong? Am I right?
You're right.
Yes, you are.
Oh, my bad. My bad.
So, I know you're gonna ask any questions. So before you ask,
Yes.
so could you go back to remember the question I asked about how do you figure out like the in the table how do
0.05?
you figure out the answer? Yeah, the 2.262.
Right.
So you said the question asked. Can you go back to the question really quick?
Yeah, sure. Right
I just
here.
want to make sure because I didn't really get it, and I thought about it and I didn't get it. So you know how it says 0.05 is the alpha, and when you go to the table,
Let me go to the table right away.
okay,
At the table, because this one is the 2-tailed test. You're gonna be looking at the one that have double prime.
right. So why don't we do 0.050, but we do 0.025? Like, do we divide it or why did you choose 0.025?
I chose. Remember, I told you you have to, because this is 2-tailed. You have to go under a double prime, which is, so that's why we'd be looking for it. 0.05.
That's why we chose the 0.050.
Yeah,
Right?
because it's
It's
alpha.
the bottom one, not the
but-
top one. That's where I
Yeah.
got it confused.
Yeah, but if the alpha is 0.05, but it is a 1-tailed test, that means you'll be looking at the top here. You will start looking for the
Right.
0.05 at the top, and it's right here.
Right. But if it's double, you look at the second one. I got it mistaken. I was looking at the top one, not the second one. Thank you so much.
You're welcome. Any other question before we conclude?
When you come down.
Yep.
At 9 in the chart, why 9?
Yeah, where is that? Oh, the here. Oh, you mean here, right?
Yes.
Because the degree of freedom, the degree of freedom is always n-1. And in this case, our n is 10.
Oh,
So
okay.
n-1 is 9. Yeah.
I got it. I got it.
Yeah, no problem. Another one? Yeah. Very good. So this one here, other ones you can see them, or it's just the same method. Like here, all you have to do is to put these numbers in Excel, find their mean, find their standard deviation, and then follow the same process we have here. And they get your test results. And for this one, it's the same thing too. Here they already give you the mean, like they give us in the previous one that we just did, and they give you the standard sample, standard deviation. You just follow the same process. Now, we're not going to do z-test for proportion at this class, but tomorrow we will now round up the class by doing correlation and regression analysis. This one, we have formulas for it. Let me introduce this topic so that tomorrow we'll just be working on the actual calculations. Now, the correlation simply means a statistical measure that tells us the extent in which two variables move together. So now, like we can say the higher the speed, you lower the time of arrival. I mean, assuming that you are not stopped by the speed cup, and that means you higher the speed, you lower the time that you arrive at the place. Or smoking and lung cancer, do they move together? Then how about this? Advertisement and sales, do they move together? So stuff like that are covered on that correlation and regression analysis. So tomorrow we start from here, and then all these formulas are just part of the formula we use for them, but we'll be using Excel.
That looks a lot.
so that you don't have to go to it. You can study this formula in your textbook, but the one with the Excel make all this, all the problems of this formula. I'll see you tomorrow. I can guarantee you we're going to have a lot of fun doing this tomorrow. Okay? All right. Any other question before we end the class?
No.
All right. Be safe, dear. Don't let the thunder, mess with you. Okay?
Down a little bit now.
Oh, hold on. Let me call your names. And then we're done. We lost Mr. Ford, so I'm just gonna check her in. Her power went off. Now I got Vista, the trouble gear that always trouble me every day. Then I get Miss Walker. Miss Walker, you still there?
I'm here.
Yeah. How about Dolly?
I'm here.
Yeah. Vanessa,
I'm here.
Keshana.
I'm here.
Debbie. Miss Debbie, I think I saw her name here. Miss Debbie, you still there?
I think it's because of the thunder.
If Miss Debbie is still alive, can you let us know? And this docket is still here.
Here.
I got everybody.
How about me? You didn't say me.
Miss Bista, right?
Yeah.
I said it first. I said that lady that give me trouble. I said it first. So I got everybody now that are here. So I'll see you tomorrow. Okay?
Have a great day.
Have a good evening.
Be safe there.
You as well.
All right. Goodbye. Okay, let's see. What's my okay, got this.